Hi all, my name is Axel and I am a PhD student in the SU Galaxy group where I work with Matthew Hayes on Lyman alpha emitting galaxies. And today I would like to present very briefly two papers that we recently wrote on that topic. The first is called the Lyman alpha Spectral Database. And the purpose of this project is to make Lyman alpha spectra available to the community. And we want, because the problem with that Lyman alpha researchers have is that there are a lot of Lyman alpha spectra observed, but most of them come from small samples and reside on individual researchers' disks. So any given person only has access to a relatively small number of these in any easy way. So we wanted to provide a place where people can upload their data and compare it to that of other people. And as part of this, we also wanted to provide homogeneous measurements of the properties of these Lyman alpha spectra. For instance, the velocity shifts of the peaks and the luminosities and things like that, so that people could easily compare their different data. So we provided this at lyman-alpha.com. You can see the database and you can go and browse through almost 340 galaxies, and where we have homogeneous measurements. And also as part of this, we developed some new measurement techniques specifically for determining the redshift from the Lyman alpha line, which is always problematic because Lyman alpha undergoes a very large amount of radiative transfer. So we had to develop a method that could easily and automatically determine a decent redshift from the Lyman alpha line. And we did this using some simple heuristics, looking at the line shapes and where they cut off and things like this. So please go and check that website out and see if you can find any useful data on it. The second paper was that came about from this project when we found out that we actually had quite a lot of Lyman alpha data which we used to populate the database, and that we could use this to really look at how Lyman alpha line profiles have changed as a function of redshift. So this is what we did, and we used samples from the COS at low redshift, so that's the cosmic origin spectrograph on Hubble, and from MUSE, the integral field spectrograph at higher redshift. And then we tried to match these samples, and then we made stacks at redshifts of 0, 3, 4, and 5, and try to see if we could deduce any shifts in the average properties of the spectra, and to see if Lyman alpha emitters are consistent with not changing very much, or if they do change a lot across this redshift range. So what we found when we did this and we compared the stacks is this figure where the black line that shows you the mean stack of the cosmic galaxies, and that shows quite a lot of emission on the left side of 0, so a blue side emission. And the colored lines, they are the stacks from MUSE, and ranging from redshift 3 to redshift 5, from blue to red. And what we found was that, okay, they also show emission on the blue side of Lyman alpha, but the amount of that emission is decreasing, or seems to be decreasing, as a function of redshift. And that's very interesting because blue Lyman alpha emission is very sensitive to being redshifted into resonance with neutral hydrogen in the IgM. So this could, or our hypothesis was then that this was the effect of the intergalactic medium absorbing Lyman alpha on the blue side as we went to higher and higher redshifts. And we wanted to test this, and we did this by getting a prescription for the average IgM attenuation from Inoue et al. 2014, and applying this to our redshift 0 spectrum, which doesn't have any attenuation in it, and then comparing the result to that of the corresponding MUSE bins. And what we found then was this, where you have the MUSE in the blue and the COS in the pink, And what we found was that if we just attenuated it by the amount of IgM we expected at that redshift from quasar measurements, the cos and the mu's actually line up really well. And so the conclusions that we then draw in this paper from this is that, well, firstly, we only need this average amount of IgM, so there doesn't seem to be a huge need for any additional absorption, which you might have expected if you expected Lyman alpha emitters to be more clustered in dense environments, for instance, at these redshifts. And the other thing that we find is that the spectral shapes on average really agree quite well between an attenuated cos and an actual high redshift spectrum, which means that the Lyman alpha line profile on average hasn't really changed across a baseline of more than 5 in redshift, which is a huge fraction of the age of the universe. So we found this very interesting. I hope you did too, and feel free to send us a message on Slack or an email if you have any questions about our papers. Thank you.